We have another special topic today, and that is Newton's method of approximation. This is section 4.8. Now this section lets us take a look into the mind of a calculator and how we program computers and calculators to find roots or evaluate roots, or simply even to just evaluate functions whenever we ask them to. And the way this works is it's basically an application of linear approximation. So the way this works is I'm going to have some function that I might not be able to calculate the root of. But what I'll do is I'll take a guess somewhere. Maybe it's somewhere easier to calculate. Or maybe I've done the intermediate value theorem and I'm choosing one of the endpoints of the interval that I found out that there exists a root on. And I'll make the tangent line just like with linear approximation. And I'll find the root of that tangent line. And that's going to be an approximation of my root. But I do it again. I'll take that x value that I found, and I'll find another tangent line. And I'll get an even better approximation of my root. And then I'll just do it again. I'll take that x value, find another tangent line, and I just kind of spiral in to wherever my root is by making all of these tangent lines. So what does that look like in terms of functions? Well, I'm going to need a tangent line, and since we're going to be repeating this process, I'm going to call my first guess x sub 0 as the first guess. I'm going to have my function, and I'm going to need the derivative of that function, and I'm going to need to evaluate the derivative of that function at x sub 0, as well as my function. So when I need my tangent line, if I remember from previous sections, my tangent line will be y minus f of x sub 0 equal to the slope f prime of x sub 0 times x minus x sub 0. So there's my tangent line, and I want to find the root of this tangent line, but that's when y is equal to 0. So I have an x-intercept when y is equal to 0, so I'll plug in y is equal to 0. I'll have whatever these extra values are. That's a minus. Times x minus x sub 0, and then I'll solve for x, and that'll give me my x-intercept. So how does this look? I'll divide both sides by f prime of x sub 0. So I'll end up with f of x sub 0 over f prime of x sub 0 equals, nope, that's negative here, and that's equal to x minus x sub 0. So when I solve for x, I get x sub 0 minus f of x sub 0 all over f prime of x sub 0. But since this is the x-intercept of my tangent line, according to what I said in the picture, I'm going to use this the next time I apply Newton's method. So I'm going to call this x sub 1. So x sub 0 is my initial guess, and I'm going to get a first approximation. But then I do it again. I find a tangent line at x sub 1, which is going to be basically exactly the same process. I'll have y minus f of x sub 1 equals f prime of x sub 1 times x minus x sub 1. And I'm going to set y equal to 0 to find the x-intercept of this new tangent line. And then I'm going to solve for x. And I'm going to get x equals x sub 1 minus f of x sub 1 all over f prime of x sub 1. And this is going to be my second approximation. Now you can see why this is going to be really, really good for calculators and computers, because all they have to do is rerun everything through the exact same function every time it gets a number. And we can write a little bit of pseudocode for this. You give it a function, differentiable, and you can either give it the derivative or you can ask the computer to find the derivative. That's fine. And then you give it an initial guess. Then what the computer does is, for as long as you want, and this could be, I want to do so many iterations, or I need you to do this until I reach a certain amount of precision, like I need to know the answer within 15 decimal places. The computer will do that if you tell it. We're going to do x sub n plus 1 equal to x sub n minus f of x sub n all over f prime of x sub n. We have this nice little recursive formula. So first, when I want x sub 1, when I want my first guess, I plug in x sub 0 on the right. If I want a third guess, first I'd have to find the second guess, because the third guess requires the second guess. So to find the second guess, I'll plug in my first guess, and I'll have a number, and then I'll plug in my second guess to get my third guess, etc., and so forth. Which is great that it's really good for computers, but Newton came from a time when they had no electricity and the world was still in black and white. So we're going to give this a shot by hand, just to see how good it really is. When we covered the intermediate value theorem, we had a problem where we asked for a solution to 3x equal to cosine of x. Now in that video, what we did was we used the intermediate value theorem, and we determined that there was a solution in 0, pi. And in fact, if we tried a little bit harder, we would have found it in 0, pi over 2. But the question here is, what is the actual value going to be? So we could try to use Newton's method of approximation on this problem. Now we've got two choices. We could either plug in 0, or we could plug in pi over 2, because these are two numbers which are easily available to us. We could choose any number in the interval, but these are already written down. So I'm going to try to choose one which is closer to what the answer should be. So if I say f of x is equal to cosine of x minus 3x, like I had before, f of 0 was 1 minus 0, and f of pi over 2 was equal to negative 3 pi over 2. I'm going to choose 0 for my first guess, because 1 is closer to 0 than 3 pi over 2 is, because pi is, 3.14? 3 of those, and you're at, 9.42 or something. And then half of that, you're still over 4. So pi over 2, f of pi over 2 is a lot farther away from 0 than f of 0 is. So if we start there, on f of x equal to cosine of x minus 3x, and the first guess is x sub 0 equals 0. Then I just run through that little algorithm I had. I have x sub n equals, plus 1 equals x sub n times f of x sub n all over f prime of x sub n. So let's set this up. My function is cosine of x minus 3x, so my derivative is negative sine of x minus 3 So x sub 1 will be equal to x sub 0, which is 0, minus f of x sub 0, so that's f of 0 over f prime of 0, which is 0 minus f of 0 is 1 minus 0, all divided by sine of 0 is 0 minus 3. So it looks like I get negative 1 over negative 3, which is positive 1/3. For decimal values, just so that I can compare later, this is 0.3 with repeating 3's. So let's try this again. My second approximation, which should be x sub 1 minus f of x sub 1 all over f prime of x sub 1 is equal to 1/3 minus f of 1/3 over f prime of 1/3, which is, of course, 1/3 minus cosine of 1/3 minus 3 times 1/3, which is 1, all over negative sine of 1/3 minus 3. Now you can see how quickly this breaks down for us poor folk who are trying to do this by hand. I mean, those are numbers. We're technically able to evaluate them. We'd have an easier time evaluating these numbers after the end of Calculus 2 when we had Taylor series to approximate these functions. But just for comparison, this number that I have written here is approximately 0.31679. Now, those two are actually pretty close together. That's close to 1/3. And I went ahead and found out what the actual solution was. It was approximately 0.316751. So, within just 2 uses of Newton's method, I actually got within, what, almost 4 decimal places of the actual answer. So if I was trying to deal with a polynomial, I would have had a great time doing this. But Newton's method also has its drawbacks. Recall, for example, that arctangent has a 0 if x is equal to 0. It's in fact the only solution. But what happens if I try to use Newton's method of approximation on this function? Well, I did some playing around with this earlier. If we start at 1, Newton's method will spiral in, because I'll go up here, I'll find a root, I'll find the tangent line, I'll find the root, I'll go back, I'll find the tangent line, I'll go back, find the root, go back up, tangent line. You know, that's great. Fantastic. However, if we start at x sub 0 equal to 2, then Newton's method will spiral out of control. So if I started up here, I would have gone, oh boy, way over here. Okay, so now I'm down here, which means I'm going to go way the heck out there. And it's just going to get worse, because this goes off to an asymptotic. This is an asymptotic function. It has a positive asymptote of pi over 2. It has a negative asymptote of pi over 2. And as I get farther off towards those asymptotes, my derivative is going to be closer to 0. And when I find a tangent line, it's going to go way far on the opposite side. And my picture is not too different from what the actual function is going to look like. So it does this. And it's terrible. And there are even worse functions. If h of x is equal to the cube root of x, for example, then there is exactly one initial guess where Newton's method works. And I bet you can guess what that is. If I guess exactly on the root, then Newton's method will turn exactly that root. So if x sub 0 equals 0, it works. Great. But it's kind of a trivial case because you're already at the root. If x sub 0 is not equal to 0, then Newton's method spirals out of control. So this is not the only method that the calculator will use to approximate roots. There are a couple of others it uses in conjunction with Newton's method. It'll start by using the intermediate value theorem. That's when you go to the graph and you ask it to find a root, and you give it an upper bound and a lower bound. And it uses a combination of Newton's method and something called the secant method, where you use two endpoints and you find a straight line between those. It's like using the average rate of change for a linear approximation instead of an instantaneous rate of change. And if those don't work, it also uses the bisection method to shrink your interval down a bunch to try to control the results of these methods. Like, for example, for my arctangent problem, if I chose too far away from 0, then I would have gotten a very bad answer, or in fact no answer at all. And for functions with multiple roots, if I choose too far away from the actual root, I might end up getting a different root altogether, which is not in the interval I was looking for. So arctangent is especially noteworthy because that means that there exists some kind of a pair of values, a positive version and a negative version, where if I try to do Newton's method on that number, I'm going to go to the negative number. And then when I use Newton's method again, it's going to bounce back to the positive number. And I'm going to have this kind of stable relationship where Newton's method doesn't go anywhere. It doesn't go in and it doesn't go out. So in addition to being able to use it for finding particular roots, we can use it to find particular function evaluations, kind of like we use linear approximation for. But we're a little bit more limited on how it works. So if, for example, we needed, well, not find, let's estimate the square root of 20. Now if I was using linear approximation, I would choose f of x equals the square root of x, and I would choose a equal to 4 or a equal to 5. 16 is a perfect square, and it's a little bit closer to 20 than 25 is, but I don't know off the top of my head which version or which initial number is going to give me a better approximation of the square root of 20. Probably 16 because it's closer, but math can do some weird things sometimes. On the other hand, I could use Newton's method, and instead of just having one linear approximation, I guess, to try to solve my answer, I can do it several times. I would have f of x equal to not the square root of x, but I would actually have the square root, not square root, I would have x squared minus 20. Because if f of x is equal to 0, that means x squared minus 20 is equal to 0, which means x squared is equal to 20, which means x is equal to the positive or negative square root of 20. So I'll just have to be careful that whenever I'm using Newton's method here, that I keep to using positive numbers. And again, I could use x sub 0 equal to 4 or x sub 0 equal to 5. Simply because it's closer, I'm going to use x sub 0 equal to 4. So what do I need out of this? Out of this I need f prime of x, and that's equal to 2x. Doesn't get much easier than that. So x sub 1 would be equal to 4 minus f of 4 over f prime of 4, which is equal to 4 minus 16 minus 20 divided by 8, which is equal to 4 minus negative 4 over 8, or 4 plus 1/2, which is equal to 2 times 4 is 8. This is 9 over 2. I like fractions more than decimals. So let's try this again. X sub 2 would be equal to 9 over 2 minus f of 9 over 2 over f prime of 9 over 2, giving me 9/2 minus 81 over 4 minus 20. Good heavens. Divided by 2 times 9 over 2, which is 9. So that's 9 over 2 minus 81 minus 80 over 4, all over 9. Fractions are the best. This is now 1 over 36, which is not very far away from 9/2, let me tell you. If I tried to make this one fraction, though, I'd need 9 times 18, and that's 162 over 36 minus 1 over 36, which is terrible. 161 over 36. Now I keep going with these, but since I'm not a robot, interesting. Oh, there we go. I keep going with these, but since I'm not a robot, let's see how good we have it. X sub 0 is equal to 4. X sub 1 is equal to, in decimal form, 4.5. And X sub 2 was about 4.4722, and the 2's repeating. So what happens when I square each of these? X sub 0 squared, that's equal to 16. X sub 1 squared is equal to 20.25. I overshot it a little bit. And X sub 2 squared is 20.00077. That's pretty dang close. And in comparison, if I take the square root of 20, I get approximately 4.4721. So in a day and age without any technology, these are the methods they had to resort to try to get very good approximations of things. And they had to do all of this by hand, and they had nothing but a stick and a bunch of dirt. But now, since we have electricity and technology and we can automate these processes, this is exactly the function which occurs when you try to find, for example, cosine of 1. So in our final video before the last test, we're going to be covering 4.9, and that's antiderivatives, which is essentially a precursor to integration. It's a hunt for functions when their derivatives are known. This whole study of that is differential equations, and antiderivatives are just a basic introduction to that, so that we at least have somewhere to start.